So, Anton, I know that you didn't want this conference to be about your birthday and so on. So let me just say a few words. As a former student of yours, a collaborator and a friend, I'm really happy to be here to not celebrate your birthday. Yeah. Okay. So I will present a joint work in progress with Edward Deryev about the volumes of strata of quadratic differentials with odd singularities. Actually, this work is a follow-up on a joint work with Vincent, Anton, and Peter Zograaf on a similar formula for the volume of principal strata of quadratic differentials. So let me begin with some notations. Oh, what? Okay, better. Okay, so I will take k to be a partition into odd integers, and I allow the ki's to be equal to -1 as well. And I will consider the stratum of quadratic differentials with singularities of order ki on genus G surfaces. Okay, so you can think of your preferred half translation surface. And mine for the talk will be this one. So let's compute quickly the stratum of this half translation surface. So if I glue the vertices of this polygon following the identification, I get one vertex of angle 5 pi. And this one is angle pi. And here you get angle pi, and here also. So you get one singularity of angle 5 pi, which is degree 3. So the degree of the singularity, I just recall that it's a number of additional half turn that you do with respect to ordinary flat point in the plane. So this is degree -1. So you are in the strata Q3 -1 to the 3, which is genus 1, as you know. And the dimension of this stratum is equal to 2G - 2 plus the number of singularities, so it's 4 in this case. Okay, so in general, these strata are complex orbifold of dimension 2G - 2 plus the number of ki's, and they are locally modeled on the C to the D via the period map. So you can think of this period map as just being the map that sends the complex number defining these sides of the polygon. So here you can choose these 4 independent sides of the polygon, and you can move them. It will give you other surfaces in the same strata. Okay. So sorry, I said Lebesgue measure. So yeah. So you get a measure by looking at Lebesgue measure on local coordinates and showing that this measure is preserved by change of coordinates. And you can define in this way the Mezervich volume of the stratum as the volume of, the measure of the set of surfaces which have area less than 1. So let me recall that you can compute the area of the surface by this formula in the flat metric induced by the quadratic differential Q by this formula. Okay. So if you are not an algebraic geometer, what you can do to evaluate these volumes is just to count integer points in the moduli space. And here, let me just say that integer points correspond to square-tiled surfaces. So I don't want to care about normalization issues. There are some. But let me just say that integer points in the stratum are square-tiled surfaces. So if you can draw your surface on a grid, we will say that it's square tiled. Okay. And we want to count such integer points to evaluate volumes. And the formula is the following. So I denote by q to the z of k, the set of integer points in the stratum q of k. And I just want to count such surfaces such that the area is less than n. So it corresponds to taking square tiled surfaces with at most n squares. You look at this number and how it grows as n goes to infinity. It grows like n to the d, and the coefficients will give you the volume. So I'm hiding all normalization issues into that constant. It's not relevant for this talk. Okay. Let me give you a brief history of the computation of such volumes, just in the case of quadratic differentials. Okay, so there is a similar story for abelian differentials. So the first computation goes back to Eskin and Okonkov that were able to show that the generating series for the counting of square tiled surfaces are quasi-modular forms, and then this gives a way to compute a volume of strata of small dimension. So I was able to implement this algorithm for strata of dimension less than 12, I guess. So it's not a lot, but still it gives some values. There are a special case when strata correspond to surfaces in genus 0. Here you can use the dynamic of the SL2R action. So since you don't get any Lyapunov exponent, you can you can compute easily the Ziegelwitch constants for this strata and get closed formula for the volumes. This is a work of Asya Eskin-Zoich. Okay, so, oops, sorry, typo here. Then there is our work with Vincent, Anton, and Peter Zograaf that express the volume of principal strata. So let me just give a little bit more notation here. As a sum over stable graph. So when I denote this, moduli space is usually the union of all strata with a fixed number of poles. So K should be a partition of 4G minus 4 plus P here. And when I talk about the volume of QGP, it's actually the Mezerwitch volume of the principal strata. So the one having only simple singularities. Okay, so I will present a similar formula for all strata. And okay, all this work was kind of in parallel. I mean, it was like the same year, basically. So the next step is the formula for, the topological recursion for these volumes of principal strata, built from the formula as sum over stable graph. And in parallel, so Martin gave a little bit of explanation about this yesterday. So Chen, Müller, and Sauvager were able to express the volume of principal strata and odd strata as some Hodge integrals, and to derive the asymptotics as the number of poles goes to infinity with the genus fixed of these volumes of principal strata. Also, Amol also computed the asymptotic of the intersection numbers that appear in our formula that I will show you later as the genus goes to infinity, and then derived the asymptotics of the volume of this principal strata as the genus goes to infinity. Also, based on the work of Chen, Müller, Sauvager, there was the result of Kazarian, Zhang, Zhang that give quadratic recursion for the volumes based on this expression as Hodge integrals. And I think, I'm not sure, but I think the last result in this direction is the work of Sauvage that gives a recursion for volume of odd strata. So actually the formula that I will present now, I mean the goal is not to compute actually volumes of strata. It's not really useful to that, but it will be useful for other problems that I will present at the end. Okay, so this is the formula. And I will, most part of the talk will be to explain what are the ingredients and to explain why is there such a formula, etc. So let me begin to explain a little bit the notations. So I will define something which is not the volume of the stratum, which is something that I will call the completed volume of the stratum, and you will see why, as such sum over stable graphs. So here in this formula, Gn and K, so K is always a partition into odd integer and -1. So this is a set of stable graphs with decorations. And these stable graphs already came up in the talk of Martin and Sam yesterday. So they are just dual graphs to stable curves in MG and bar. Okay, so for instance, I can consider this nodal curve. And I consider the dual graph. Like this. And actually, I want to put more information. So I will think of this, I will think of these nodal curves with an additional stable differential on them. So I will record the order of singularities that I see at the marked points. Okay, so I want to decorate this stable graph with what will be the order of singularities of quadratic differential on that. So I can also, since the poles will play a special role, I can just mark the pole specially with some legs. But this is not really important. So this is a set of stable graphs that I'm summing on. Then I will show you how to construct P gamma, which is a polynomial in the variables bi's that depends on the graph, gamma, so gamma here, and that depends on some other set of polynomials that I will define later. Okay. So I will show you an example to see how this formula works. And finally, the last ingredient is this operator Z, which is a linear operator on polynomials that sends the product of bi to the di to the product of di factorial zeta of di plus 1. So to each monomial it associates a number. Okay, so this is the first line of the formula. I define some quantity to be equal to this sum over stable graph of the, okay, let me just write again this formula here in a more compact way. So this thing, which I call the completed volume of the stratum, is some normalization constant times the sum over all stable graph G and K of some polynomial, and I apply just some linear operator on this polynomial. So basically, this is the first line of the formula. And then the second lines just tell you that actually this sum doesn't give you the volume of the stratum, but it gives you the volume of the stratum plus some additional terms that I will explain later. So you see appearing a linear combination of volumes of basically boundary strata, so product of abelian strata, minimal abelian strata, and other odd quadratic stratum. And I will explain what are these coefficients. And basically, so I didn't write all the conditions that you see in the sum, but basically what I ask is that, first of all, this strata makes sense, okay? And then that the dimension of the product here is the same of the dimension of the initial strata. So I'm really emphasizing here that I don't work with projectivized strata. Okay, I work with the regular strata, so the dimension is really the sum of the dimension of the strata. Okay. Okay, so let's just see what gives this formula in some simple example. So here I need these polynomials that I will define in a moment. So I just give you these polynomials. You see that already that they are symmetric, homogeneous, and even degree polynomials. Okay. And I want to list all decorated stable graphs that correspond to the decoration 3 minus 1 minus 1 minus 1. So the goal is to compute the volume of this stratum. So the claim is that there are 3 such stable graphs. So this is one of them. But there are 2 other ones. And to each such stable graph, what I do is, first of all, I put a label on the edge. So here it's B1, here it's B1, here it's B1, B2. Then to each vertex, I will associate the corresponding polynomial where I replace the variables by the labels that appear here in the edges. So here I see the label B1 and here again B1. So I take this polynomial and I apply it to B1, B1. And here this parameter just corresponds to the decoration of this vertex that I get here. So I can do the same here. For this vertex, I get this polynomial. For this one, I get this one, etc. Then I multiply by the product of bi's. So here there is only one B1, etc. Here there is B1, B2. I have an additional factor, which is the automorphism of the graph. So, okay. So here I get 1/2 order 2 automorphism of the graph, etc. So I get this factor. And then I get a polynomial, and then I apply my operator z and get some number. Okay? And I consider the sum. So here the sum is just 2 pi 4 over 3. So it's not the volume of the stratum 3 minus 1 to the 3. But it's the volume of this stratum plus some additional contribution. And it's okay, it works. Okay, nice. So I will come back to this example after I explain why do we have such things, etc. What are these polynomials, etc. So let me define properly this polynomial ngn to the k that appear here. Yes.
Just going back to the formula.
Yeah.
I just want to check. So this volume product at the last line of the formula, so the total genus really concentrated there. In other words, you allow maybe one single odd zero to go down with a
No, many odd zeros to go down.
Many odd zeros.
And the other stratum are here to compensate the loss of the genus in somehow. Okay? Okay, I will show, I mean, I will explain better later, so it will be clear, I think. Yes?
So when P formula is either in
P? P is this polynomial. No.
There's the number of poles.
Ah, yeah. So I didn't, okay. Where is P? It's, I mean, it will be here. No, not here, sorry. It will be hidden here in the decoration, okay? Of the polynomials, okay? Yeah, they are hidden in K. All the poles are hidden in K. Okay. Okay, so let me define these polynomials that I will call Kontsevich polynomials. And I need to go back to ribbon graphs. So we saw already ribbon graphs in the talk of Francisco yesterday. So you can think of them as graph with a cyclic ordering at each vertex. Or you can think of them as graph embedded in surfaces. So this is how I choose to look at them. So yesterday, Francisco explained a way to, a correspondence between metric ribbon graphs and the spine of some hyperbolic surfaces with boundaries. So here I just want to focus on the correspondence of ribbon graphs with Jenkins-Strebel differentials. So I will focus on the result of Strebel that gives this correspondence. So let me recall that metric ribbon graphs are just ribbon graphs with data of a length on each edge. So okay. So what is this correspondence? If you start from a metric ribbon graph, to construct a Jenkins-Strebel differential, you can just glue infinite cylinders, infinite flat cylinder, Euclidean cylinder, to the boundary of this, to the faces of this graph. So like in the picture here. And this gives you a Jenkins-Strebel differential, quadratic differential. Okay. And in the other way around, you can start with some Jenkins-Strebel differential and look at the critical graph, like the set of all saddle connections of this differential. And this gives you graphs that are naturally embedded in the surface, so it gives you ribbon graphs. And there are also a notion of length of these saddle connections, because you have the flat metric. So you get really a metric ribbon graph. Okay, so the Strebel theorem gives you actually a homeomorphism between the moduli space of curves times r to the n, the set of positive number, to the combinatorial moduli space, so the set of all of equivalence classes of all ribbon graphs, by this map. Okay, so the BIs that correspond to the lengths of the faces of this graph are just the perimeter of the cylinders, or you can think of them as residues of the double poles of the differential. So there exists a natural compactification of this combinatorial moduli space by considering stable ribbon graphs. You know about the Döhling-Mumford compactification of MGN by stable curves. So you can try to extend this map to the compactification. Actually, you have to be careful because the extension of this is not one-to-one. What is the issue here? The issue here is that when you consider stable curves in MGN bar that have some components without mark points, you don't see them in the critical graph. Yeah. So you need to forget about these components to make this to extend this homeomorphism on this compactification. So actually, I will hide the technical point, but actually, the extension is not to the compactification, but rather a quotient of this Döhling-Mumford compactification. Okay, but whatever. I will just pretend that it is the case. And now, okay, I will come to the definition of these polynomials. Now, let me just define the coefficients of these polynomials. So I can consider a sequence of non-negative integers, mi, and look at the set of ribbon graphs that have exactly mi vertices of valency 2i plus 1 and n boundaries. So I denote this subcomplex by m star n. And if there are no univalent vertices, this is really a subcomplex of the combinatorial moduli space, and you can compute its codimension in terms of the mi's. The work of Kontsevich gives you a natural orientation on the components of this complex, so you can construct like this a cycle in the combinatorial moduli space, and using this Strebel map, you get a homology class that I will denote by W m star n on mgn bar. So here I hide the technicalities. Okay, so the definition is that we look at the intersection numbers of the psi classes along this cycle and denote this intersection number with the notation tau d index m star. So if you don't know what are these classes, it's not a big deal because I will explain to you how to compute these numbers, actually compute them. And I define the polynomial ngnk to be the polynomial where the coefficients are just these particular intersection numbers. Okay, so a long definition, but what is the interest of this polynomial? It's this result of Kontsevich. Actually, this polynomial counts integer metrics on the ribbon graphs that you are interested in, okay? So if I want to be, more precise, sorry, sorry, I'm lost in my slides. Okay, where are this? No, I don't see the. Okay, sorry for that. Okay, so this polynomial, so this is a legit polynomial, is equal to the counting function of integer metric on such ribbon graphs, plus lower order terms. So what I mean by this formula is that this counting function is actually a piecewise quasi-polynomial. And I'm just saying that this piecewise quasi-polynomial agrees with this polynomial on the chambers and for the BIs that satisfy this condition. Okay, so on certain subset of the parameter space, it really counts the number of integer metric on the graphs. Okay, let me go to an example because this is kind of, oh, no, not yet, sorry, not yet. Okay, I want to say before that how to compute these coefficients, these polynomials. So let me just give a few results about these numbers. So you can build the generating series for these numbers. You have two sets of variables, the variables that correspond to the power of the psi classes, basically, and the variables that correspond to the valences of the vertices of the graph, the mi. So if you restrict to the variable, to the point 0, 1, 0, actually you recover the classical generating series for the classical intersection numbers of psi classes on mgn bar. If you want to compute these coefficients from the generating series, what you want is really to compute SI derivatives of this series and to consider this series at this point, okay, to kill all S variables. Okay, so what is known about this generating series? First of all, Kontsevich showed that the exponential generating series is actually an asymptotic expansion of some matrix, typo here again, matrix integral. And actually right after that, DeFrancesco, Dixon, Zubert showed that there is a way to relate the S derivative of this function at this point in terms of the T derivatives. And the T derivatives are just at this point, are just the classical intersection, the coefficients of this function are just the classical intersection number. So basically, such a formula gives you a way to compute these coefficients in terms of the classical ones. So in their paper, there is a very explicit construction of this linear isomorphism that allows to implement this correspondence and compute things. Okay. Okay, let's do an example. Yes. To see what this polynomial looks like. So I will focus on this case. So k is 3 minus 1. I am in genus 0. So I want to actually compute the number of integer matrix on genus 0 ribbon graphs with one vertex of valency 5 and one vertex of valency 1. And I get 3 faces that have lengths B1, B2, B3. See, so if I lost you with the notation before, you can go back here. It's just an example. So let me do the list of such graph. There are only 2, this one and this one. If you try to draw ribbon graphs of genus 0 with such constraints, you get only 2 graphs. So if you want to count the number of matrix, it's kind of easy to do. You look at the contribution of these graphs. So how many ways I can put lengths on these sides such that the boundary components have lengths bi, bj, bk. So the only condition that I have here is that bi should be strictly greater than bj plus bk. If I have this condition, then I can choose this length to be bj, this length to be bk, and this length to be the difference over 2. So everything is determined up to this condition. So actually, the contribution of such graph, you can read it in the simplex where all bi's are positive in this chamber. So this chamber is just the chamber where bi is greater than bj plus bk. And here you have a contribution equal to 2 because you get 2 such graphs. When you label the faces, you can do the other way around. So you get 2 contributions. You can work in the same way for these ribbon graphs and see that they contribute 1 in this chamber. And you just sum up everything. And you get that the number of integer matrix on such ribbon graph is equal to 3 in all these chambers. Sorry, I'm not sure that the picture is really clear, but in all these chambers, the number is equal to 3. And you have some other values on the walls. So here, for instance, in this wall, you only see the contribution from this type of graph. So the value is just 2, actually. And I claim that the polynomial, if I compute this Kontsevich polynomial using these intersection numbers, etc., I get 3. So this is just to show you that this polynomial really coincides with the number of integer matrix inside, in the chambers and not on the walls, right? So what is the difference between this polynomial and the counting and the legit counting function of integer metric? For instance, here, the missing coefficient 1 would be the contribution of the number of integer matrix on such graph. So here you see that we are on the wall where b1 equal to b2. Say that this is 1 and this is, this bj is b2. So this corresponds to the wall where this loop, okay, let me just do the example, it will be easier. Sorry. 1, 2, 3. So if b1 equals to b2, it means that the length of this edge is just 0. Okay, so it's not anymore a ribbon graph with odd valences. It's a union of ribbon graphs with some even valences, etc. Okay, what I see when I take this length to be 0, I see this component and this component. And basically, the difference between these 2 countings is just the number of matrix on this kind of degenerations. Okay, I should hurry up. So let me, now that I have all ingredients, give you the kind of the idea behind the formula. So recall that I want to compute volume of strata. So I want to count the number of integer points of square tile surfaces. The first remark is that once you get a square tile surface, it always decomposes into horizontal cylinders. So this is another square tile surface in the same stratum. So I just moved a little bit this complex number, but I claim that this is also a square tile surface. Okay. So the thing to notice is that I can encode the decomposition of cylinder into these stable graphs. So one way to do that is just to pinch the waist curves of the cylinders. You get a nodal curve, and this nodal curve corresponds to this stable graph. This is one way to do that. You can also cut along these waist curves and look at the connected components that you get. Actually, the connected components that you get are just ribbon graphs, because you get the boundary of cylinders, that is a graph of horizontal saddle connections, plus a small neighborhood in the surface. So it's really a ribbon graph here. So I'm just doing here the components of the surface after cutting along the cylinders. So you see I get these two ribbon graphs. So I can encode I can declare that the stable graph, the vertices of this graph correspond to the connected components of the cutted surface. So actually ribbon graphs. And here the decoration gives you just the valences of this graph. Okay. And then the edges of this graph represent the cylinder that are glued to this connected component. Okay, so here I get one big cylinder of length B1 and one smaller cylinder of length B2, which is glued on these two faces. Okay, yes?
Does it matter on your slides that the valences are odd?
Because I know how to count integer matrix on odd ribbon graph. This is the only thing.
You know how to count?
The number of integer matrix on this kind of ribbon graphs.
Odd.
Odd, yeah. The things that I mentioned before are true for odd valences. Okay, so if you want to count such surfaces, you want to know how many integer parameters you can choose for the length of these saddle connections, for this one, for the BIs, for the heights of the cylinder, for the twist of the cylinders. So everything is kind of easy to handle. The only thing which is not easy to handle is the choice for the length of these horizontal saddle connections. But the choice of the length of this horizontal saddle connection is just the choice of integer matrix on this ribbon graphs, right? And this is already done for us, okay? So the result of Kontsevich tells you that if you want to know how many choices there are to put integer lengths on this one, on this kind of ribbon graph, you get some polynomial, etc. And you can compute this polynomial. So basically the formula comes from that. So why do we have some additional contribution? So maybe you begin to see why, I hope. But let me go back to the example of the computation of this volume. So as I said, I have three types of stable graph. And now you know that these three types of stable graph correspond to three types of decomposition into cylinders. So this is a one cylinder square tiled surface. So I just drew the topological picture here. You have only one cylinder which is glued to himself along this kind of ribbon graph. This is another type of one cylinder surface. Here the cylinder is separating now. And so it's glued to this ribbon graph on one side and this ribbon graph on the other side. And you get this kind of surfaces with two cylinders that are glued like this way. Okay, so now this polynomial really gives you the number of metrics that you can put on the ribbon graphs such that the lengths of these faces are equal to B1 and B1. So I want the length of the faces to be equal to be able to glue cylinders to them. Okay? And here you can notice, for instance, that I want the faces to have length B1 on one side to glue a cylinder of perimeter B1, and length B2 and B2 on the other side to glue a cylinder of length B2 on the two faces of this graph. So this is why we get such polynomials. And now I want to come back on this difference between these two computations. Let me first give you the actual formula. So the story here is a bit funny because 1 year ago in Oberwolfach I presented this work in progress. It was already in progress yet at this time, and I presented a list of examples of small strata with some coefficients appearing that we couldn't explain at the time. And Adrien Sauvaget just, like in a few hours, came up with this formula, which is very nice, that I want to explain a little bit. And we checked, and actually it was true, and now we are able to explain actually this formula. And the proof is almost complete, up to some combinatorial identities that I need to prove. So what is this formula? It's a really funny story. So we have this number, the completed volume of the stratum. And for now, I just want to declare that this behaves as a multilinear function on the variables k1 with a bar. I'll just declare that this is a product of some variables that I denote by this. Okay? And I also declare that the volume of the product of the stratum here is the product of other variables without bars. Okay? So this doesn't make sense for now. But then how to compute the coefficients appearing in the formula? You just declare that you have the following change of variables. So the variables k bar that appear here are in fact just linear combination of this variable k with this kind of coefficients. And the coefficients that we were trying to explain for a really long time were these nice double factorial coefficients appearing here. Okay, so in my example, if I want to compute the completed volume of 3 minus 1 minus 1 minus 1, so I do as all these integer ki's were independent. Okay, so, oops. So I declare that this is just these variables times minus 1 completed 3 times. I claim that this is just equal to this product. And I replace 3 completed 3 by its value. So it's the regular 3 plus, here the coefficient is pretty simple. It's just 1, this coefficient. So you only see 0 times 1. And I multiply by this. So I should say that minus 1 completed is just equal to minus 1. Okay, so I get minus 1. And basically, it tells you that if I go back, it tells you that this is equal to the volume of the stratum Q3 minus 1 to the 3. So this is this product, plus the volume of H0, this one, times, oh, sorry, this is a minus 1. Yes, times Q minus 1 to the 4. Okay, and you get your formula. So this is really funny, I think. And okay, why do we get such a formula for these coefficients? Okay, so this is again the computation for the example. So I have completed 3. I did it here. Okay. So where does the coefficient come from? So what I explained to you before is that in the formula you get some polynomials involved that count integer matrix on ribbon graph outside some walls. Okay? So they really count what we want, but not everywhere. There are some walls in the parameter bi's where it doesn't count what we want. So if you look at the polynomial corresponding to the counting of matrix on this ribbon graph, we've seen that on the wall B2 equal to B3, we actually count integer matrix on this degenerate ribbon graph, okay, which is not anymore a ribbon graph with odd valences. It's a product of, it's a union of ribbon graphs. Okay? So it means that when I plug this polynomial in my formula, I will also count contribution coming from this kind of degenerations. So in particular, in this type of square tile surfaces, the one which has two cylinders, here I am interested in ribbon graphs that have two faces which equal length. I want to glue a cylinder to these faces. So I am really working already on a wall in terms of the BIs. So what I am counting in this wall is additional terms coming from these degenerate contributions. So I'm counting actually contribution of H0 and contribution of Q minus 1 to the 4. Okay. Don't know if it's really clear or not, but this is the idea behind these coefficients. Do you have questions so far before I go to the idea of the proof? Yes.
I guess so the constant coefficient you're getting is somehow capturing gluings.
Exactly, but it's a mess, basically. But it's a mess, and there is one miracle is that at the end you get only this double factorial. Once you sum over all this mess, you get only double factorial. So this is what, yeah. So yeah, yeah.
Sorry, I still want to go back to my earlier question about interpretation in terms of the PCGM boundary strata.
Yes.
Think of your formula have some quadratic strata on top together with a abelian strata.
Yeah, this is only the strata on top, yes.
And you said some zeros will go down, like in the two-level graph.
Yes.
And may I?
No, not. I mean, yes, that's right. So you will see the odd, yeah.
Okay, so
yeah.
the bottom vertex should be of genus 0.
Yes, yes,
Then
yes,
I
exactly.
think some of the coefficients should come from the psi class product for the mark point zeros that go down, right? If you think of in some sense.
Yeah, probably. So I'm interested I mean, I try to understand these coefficients as something with the compactification. So I'm interested in talking to you later about that. Okay, because I had some issues with the fact that I don't work with projectivized strata. So there are something about the dimension and so on. So it's a bit, it's not that obvious. Okay, so what is the idea to combinatorially compute these coefficients that I see in here? The first remark is that we really want to work with ribbon graphs. Once we know what happened for the degenerations of ribbon graph, we know what happened for square tile surfaces, basically. And what we want to do is to evaluate the difference between the polynomial that we know how to compute and the actual counting function for the matrix on these kind of walls. So I can have several equations like this. Okay, and this is really the goal. And the first remark is that the only contribution that will appear, so I'm only interested in the higher order terms in this polynomial. So the only contribution that really are seen on this wall, they came from pinching separating loops, like exactly in this picture. And I want to pinch a separating loop that separates some abelian components. So what I call abelian components. So here I just pinch this loop, and you see that it separates this component. So why I call it abelian? It's just because the Jenkins treble differential corresponding to this ribbon graph is actually abelian. Okay. And you know that why we get the same degree of polynomial here in the degeneration is because the dimension of abelian strata are one more than the dimension of quadratic strata, more or less. Okay, great, thank you. So the only contribution that you have to take care about is pinching the separating curves. There can be a lot of them that separate abelian components. And then, since I have 5 minutes, I won't detail the further steps, but to complete the proof, we just need to prove two nice combinatorial identities that relating the number of choice of sectors, etc., and gluings of all these degenerating things with these double factorials. Okay, so you can ask me for details if you are interested. Okay, so now that I spent most of my time explaining this formula, I want to sell it to you. I want to sell it by saying that the similar formula in the case of principal strata had a lot of consequences in the large genus asymptotics. So first of all, there was this work of Amol to compute the large genus asymptotic of strata. But now with the advances of the algebraic approach to these volumes, I'm not sure that it would be the best way to get these asymptotics, but still we get nice results because you see this formula separates the contribution of surfaces that have one cylinder, surfaces that have two cylinders, etc. So you can analyze really in details the contribution of this kind of surfaces with respect to this kind of surfaces. So for instance, in the case of principal strata, and I assume that there are no poles, you can compute the contribution to the volume of the square-tile surfaces that have one cylinder which is separating, so this is this quantity, and compare this to the contribution of square-tile surfaces with one non-separating cylinder, and compute the large genus asymptotic. So you will just study the corresponding stable graph and the contribution of this stable graph and compare them. And thanks to the work of Amol, we get that this contribution is, with high probability, you only see non-separating one-cylinder surfaces, for instance, as the genus goes. You can also study the proportion of one-cylinder surfaces among all square-tile surfaces and see that it goes as 1 over square root of G. Also, you can study actually the distribution of the number of cylinders, and there is a nice result that say that it converges in some sense that I don't want to detail here, to some Poisson distribution of parameter log of the dimension, basically, over 2. Okay. And another type of result that you can get is that, for instance, when you look at large genus square-tile surfaces with high probability, you will see all singularities on the same layer. It means that when you cut the surface along the cylinders, you get only one connected component as the genus tends to infinity. So all this you can analyze through the formula via the sum over stable graph. So what are the hopes for the future? So I will be brief about that. A conjecture is that all these results that I mentioned before will continue to hold for odd strata, at least when you fix some finite number of odd singularities and you complete with a bunch of simple singularities once, and you let the genus tends to infinity. Okay, so a first step in showing such conjecture is to notice that if you look at the cylinder, the contribution of one cylinder surfaces, so you have this completed volume, this not completed volume. Actually, when you look at one cylinder surfaces, it's the same contribution in both sides. So you don't have to care about this mess, about these coefficients, etc., these degenerations. So for one cylinder, it's pretty nice. But of course, the work to do is to compute the asymptotics of this these intersection numbers as the genus goes to infinity. So this is, I don't know, I need to discuss with Amol if he's interested in doing that. But yeah, okay. So, and now a wild guess is that actually these intersection numbers that appear in the formula will behave asymptotically as the classical ones. at least when you fix some of the MIs. Okay. So there are more conjecture I will be happy to discuss with you, but I will stop here for today. Thank you.